Good morning, everyone. This is Shauna, and I'm coming to you today to make the first of what I hope will be a series of videos on related rates. This is a topic from calculus and sometimes business calculus that really poses a lot of difficulty for students, whatever level they're on. So I wanted to try and make a video to try and demystify some of this process. I'm going to put an example problem on the whiteboard. Let me share the whiteboard at this time. And I'm going to put up a pretty basic problem. This is not as hard as they could get, but just to get us started with discussing this. Let's say we have this. So the radius of a sphere, is increasing at a rate of 2 inches per minute. Find the rate of change of the volume when the radius is 6 inches. Okay. Now, I hope to, in this video, give you some principles that you can use to solve problems that are harder than this, and hopefully I'll get a chance to show you some in future videos. But the way related rates work is we have 2 or more. It doesn't have to be just 2. In this problem, it's just 2. We have volume and we have radius. But you can have more than 2. Sometimes you have to come up with extra rates. But the goal of a related rates problem is to find the rate of change of something that is changing with respect to time. So our goal in a related rates problem here, our goal is to find an unknown rate of change with respect to time. That's always our goal in a related rate problem. Sometimes, as I said, there are more than 2, and sometimes you're looking for more than 1 rate, but you have at least 1 unknown rate of change that you're looking for. And the way we do it, this is why you had to study implicit differentiation first. The method is to differentiate every variable implicitly with respect to time. That's our method in a sentence, okay? That's usually not the hardest part of the problem. Before you can actually differentiate each variable, you have to find the relationship. So when you're doing this, you have to find the relationship. I purposely chose this problem because the relationship is fairly straightforward and we don't have more than 1 here, but you can. So in terms of the setup that you're going to have, we're going to follow a setup idea. So setup. When you do the setup, as we do in other word problems, we're going to do some things. The first thing we're going to do is look for keywords. And I'm going to explain to you, we have all the keywords that we've always had, sum and difference and quotient and all of that, and volume and different things. But we also have some new ones for related rates. So we look for keywords. What I like to do is label. This gets more important as you get more rates, more variables. But I like to label all the variables and all the rates, okay? And then this is the part that usually is problematic, is this third step. This third step is the whole crux of the idea. Assuming that you've correctly identified everything in step 2, the third step is to look for relationships among variable. Okay, that's the issue there. You look for relationships among the variables. And so, oops, I misspelled the word here. Let me go back. Look for relationships among variable. So that's our next step. And I'm going to show you that in a minute. So here, now, and then you write an equation and then you employ the method. So you write an equation as we would do. We're going to step 4. We're going to write an equation. Sometimes you need more than one. And then we're going to employ our method for solving the problem, okay? And I'm going to show you that in a separate, we're going to solve for the unknown rate, okay? So that's my setup. So I have a goal, I have a method, I have a setup. Now, when you solve, I'm going to come over here, okay? There's a whole situation we do, okay? So I'm going to come over here and I'm going to show you this on this problem here. So I'm going to come over to this other whiteboard and I'm going to write the problem again for the sake of clarity, and we're going to solve it. So we have, it says, the radius of a sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the volume. Find the rate of change of the volume when the radius is 6 inches. Okay. So the first thing I'm going to do, and you can streamline some of this process once you know more about it, but for the sake of clarity, I'm going to do the whole thing. So the radius of a sphere, okay? So I know that I have a sphere here, okay? So I'm going to draw a sphere, my best impression of a sphere that I can muster. Okay, there's a circle, and I'm going to sort of augment my circle here with some, if I can find, there it is, if I can find the drawing tools. Hold on, I messed this up. Let me come back. There it is. I want to find my shapes. Let me see. I'm gonna draw now. So I'm gonna draw a little bit, and this is gonna be tricky on Zoom, but I'm gonna try and draw this so that you can see that it looks like this is not really very possible for me on Zoom, but I'm doing the best I can here. So this is my sphere, okay? And they've given me a radius. Now, the first thing I'm gonna do is I'm gonna define everything. So I'm gonna say, and you'll see why I need to define this in a minute. Let V equal the volume of the sphere. And I like to put units in, this is gonna be cubic inches, okay? Cubic inches, okay? And I need R. So I'm gonna say let R be the radius of the sphere in inches, okay? Now, all of those variables are going to have rates attached. So I'm going to write this. All of my variables in a related rates problem will have rates attached to them. So dv dt is going to be the rate of change of volume with respect to time. Now, sometimes this will change with respect to other things too, but in this case, it's only changing with respect to time. And dr dt is the rate of change of the radius with respect to time, okay? Now, sometimes you have constants in these problems, like so things that are in the problem that don't change. Like, for example, the length of a ladder. If the ladder's moving down the side of a wall, which hopefully I'll have a chance to look at in another video, the length of the ladder is not going to change. So that's a constant. That doesn't take a dt. We can make it that, but we don't have to. Once you have this situated, okay, this is you're ready to set it up. So it says, okay, in terms of keywords, because I promised you that I would talk about keywords here, and I'm going to do that. So this becomes, I'm going to come up here and I'm going to stop sharing for a second and reshare the screen here. Now, my keywords, we already talked about. We need radius. We have a sphere, right? Now it's increasing. Increasing means that this is going to be positive, okay? This is going to be positive. Increasing is another word for positive. At a rate, okay, there's my keyword. This is one of those keywords. When you see a rate like this in a related rate problem, this is going to mean derivative. Okay, it's a derivative. Now, it says, find the rate of change. Oh, okay. So here we have find the rate of change. So we're going to, here's another rate of change over here, right? There it is. Find the rate of change. Again, this is a derivative, right? So it's the derivative of the volume. Okay, well, G, here I am, right? Derivative of the volume. Okay, I know how to do that. I have it right here. Derivative of the volume, dv dt, when the radius is 6 inches. So the first thing in terms of setup is your picture and your variables. So the first part of your setup is the picture and the variables. The next part of this is, so we have, this is step 1, and it's picture and variable. Step 2 is going to be our formula or equation. Okay, sometimes it's not a formula from geometry. This one happens to be a formula. If you don't remember it, look it up. We're relating volume of a sphere to the radius. And so what's happening is maybe you're blowing up like a circular balloon, and as you blow it up, the radius is increasing, right? So the radius of the sphere is increasing, and so the volume of the sphere is also increasing because the sphere is getting bigger, so the amount of space it holds is larger. In any case, the volume of a sphere is going to be this. So we have volume V, and I'll go back to the blue here. I'll go back to this blue color. So we have volume. Volume is equal to 4/3 pi r to the third power. That's our volume formula. Now, this is V equals, let me go back. You know what? I forgot my equal sign, so let me just fix this one more time. Volume equals 4/3 pi. Cute. Now, the next thing you're going to do, is you're going to differentiate everything with respect to time. This is your implicit derivative. So you differentiate every variable with respect to time. Okay. So you get dv dt, and again, I'll go back to the blue here. This is going to give me dv dt is equal to, remember 4/3 and pi are both constants, so I'm going to bring them out, 4/3 pi, and I'm going to differentiate the r cubed, that's 3r squared, 3r squared. That's my derivative of r. But now this is an implicit derivative with respect to time, remember. So what I'm going to do here is I'm going to take this 3r squared and multiply it by dr dt, because it's an implicit derivative. Okay, so there's my equation right now. Okay, find the rate of change of the volume. So what do we want to do here? We want to now, at this point, when you're here, now you want to substitute, okay? You want to sometimes people will take this equation. Now I can simplify, and actually I think I'm going to do that first. So I'm going to simplify here next. So step four is to simplify, okay? Simplify my equation. You may have to rewrite some stuff. You may have to substitute some values. It may be a lot of things, but I like to try and simplify as much as I can. So here I'm going to say dv dt is equal to the 4/3, the 3 and the 4/3 and the 3 on the pi, the r squared, sorry, simplify, they cancel out. So I end up with 4 pi r squared dr dt. Okay, so not much to simplify here, but nevertheless, there we go. Now, find the rate of change of the volume when the radius is 6 inches. So remember, we want to find the dv dt. So I'm set up to do this. And again, I chose this example for a reason. What am I doing here in terms of my setup? Well, I'm going to come over here and I'm going to say dv dt, I don't have. That's my question. I know R at the time that they're telling me, R is 6 inches. They told me that. They also said that it's increasing, dr dt, the radius is increasing at a rate of 2 inches per minute. Okay, that's my little setup. So it's just about plugging it in here. So what I'm going to do next is I'm going to, step 5, I'm going to do this. I'm going to say that my next piece is going to be the following. I'm going to set it up, plug everything in, and solve it. So you have 2, I'm sorry, you have dv dt. So this is dv dt is equal to 4 pi, r, remember, is 6 squared, and dr dt is 2. When you do that calculation, you're going to square 6, that's 36. 4 times 36 is 144. 144 times 2 is 288. So dv dt is 288 pi cubic inches. remember this is a rate, so it's cubic inches per minute. Okay, so dVdt is 288 cubic inches per minute. I hope that this video has been helpful to you. And I'll see you in my next video. Thank you, folks. Bye for now.